In the name of Allah, in this lecture, I will discuss the difference between the zero sequence current and the neutral current. I will also answer the question, is the zero sequence current AC or DC? Additionally, I will discuss the positive sequence current, negative sequence current, and especially the zero sequence current in star and delta connections. Of course, without a doubt, we must understand that the zero sequence current is an alternating current AC. It is important to note that the zero sequence current consists of three-phase vectors that are equal in magnitude, just like any regular three-phase network. However, the only difference is that the angle between any two phases is 0 degrees. This means that all three phases, R, S, and T, are equal in magnitude, have the same direction, and the phase angle between them is 0 degrees, effectively behaving as a single-phase AC system. The second important point is that, as we will discuss shortly, the zero sequence current flows through the neutral line that is connected to the ground. Additionally, we must understand that the current transformers, CTs, installed on the neutral line can sense and measure the zero sequence current. Of course, we all know that a current transformer measures alternating current, AC, and not direct current, DC. Next, we will discuss a very important point: how the positive sequence current, the negative sequence current, and especially the zero sequence current behave, manifest, or take form in transmission lines with delta and star connections. First, it is important to understand that the symmetrical components method is strongly affected by whether the neutral point is grounded or not. It is important to emphasize that this specifically applies to unbalanced fault calculations. This means that in the case of symmetrical faults, be it a three-phase fault or a three-phase to ground fault, we observe that the current in the neutral line is 0. This means that the neutral point configuration, whether grounded or ungrounded, has no impact during symmetrical faults, as no current flows through the neutral line. Therefore, we must understand a very important point. The positive sequence current always appears in the electrical network as the system's normal operating current. This means that the positive sequence current is present in the network both before and after a fault occurs. Another key point is that positive sequence currents are present in both symmetrical and unsymmetrical faults. As for the negative sequence current, it appears in two cases. The first case occurs with unbalanced loads, meaning the values of the loads on the three phases R, S, T are different. This, of course, causes varying current values to flow through the three phases R, S, T, leading to unbalanced current. The second case is the negative sequence current appears in unsymmetrical faults, and as we have learned in previous lectures, the different types of unsymmetrical faults. As for the zero sequence current, which is an alternating current with three equal phase magnitudes in the same direction and with a 0 degree angle between them, the zero sequence current occurs when current flows to the ground, that is, during a ground fault or earth fault. It has been explained earlier that an unsymmetrical fault or current is analyzed into positive sequence current, negative sequence current, and zero sequence current, with this analysis being applied to each phase. Therefore, each phase, whether R, S, or T, has a zero sequence current. Thus, the zero sequence current for each phase, R, S, or T, is summed and flows together through the grounded neutral point. Therefore, we can say that the neutral current value is the sum of the zero sequence currents for the three phases, R, S, T. This means that the neutral line current in the case of earth faults or ground faults is 3 times the zero sequence current, or in other words, the zero sequence current is equal to the neutral line current divided by 3. It is known that the zero sequence currents are equal in magnitude and direction, meaning that the zero sequence current for phase R equals that for phase S and the zero sequence current for phase T. Therefore, we say that their sum is 3 times the zero sequence current. We also need to understand that the zero sequence current is the only symmetrical component that can be directly measured using a multimeter by measuring the current flowing through the neutral line and dividing it by 3. It is important to emphasize that the zero sequence current only appears in the case of unsymmetrical earth faults or faults where the ground is part of the fault. This is because in the case of a symmetrical ground fault, no zero sequence current will appear. Therefore, we can say that if symmetrical faults occur, only the positive sequence current will appear. But if unsymmetrical phase faults or phase-to-phase faults occur, both the negative sequence current and the positive sequence current will appear. But if unsymmetrical earth faults occur, whether single phase to earth or phase to earth, the negative sequence current, positive sequence current, and zero sequence current will appear. Therefore, we can say that the only current that flows between the grounded neutral point and the ground is the zero sequence current, which is the sum of the zero sequence currents of the 3 phases, R, S, T. Thus, the current that will flow through the neutral line is 3 times the zero sequence current. However, it is important to understand that the negative sequence currents and positive sequence currents do not flow between the neutral point and the ground because they are symmetrical currents. The second point is that the delta connection does not allow the flow of zero sequence currents in the lines connected to it. However, the zero sequence currents remain confined and circulate within the delta windings and do not flow into the connected lines. The third point is that in the case of an ungrounded neutral point, the zero sequence current does not flow in the lines connected to the star connection. However, the star connection allows the flow of positive sequence current and negative sequence current in the connected lines. Everyone knows that in the case of a star connection, the voltage between 2 phases or line-to-line voltage is referred to as line voltage, and the voltage between any phase and the neutral line is referred to as phase voltage. Therefore, we observe that in the star connection presented here, no zero sequence voltage appears between the lines, despite the fact that zero sequence voltage exists in the phase voltage between the phase and the neutral. Now, let's discuss the difference between zero sequence current and neutral current. Everyone knows that if we have a single phase load, it will have 2 terminals. One terminal is connected to any phase, let's say phase R, for example, and the other terminal is connected to the neutral line. Therefore, since the circuit we have is a single phase circuit, the current flowing through phase R is the same as the current that will flow through the neutral line. However, it is important to understand and emphasize that this is true under normal conditions. Therefore, it is incorrect to refer to the current in the neutral line, in this case, as zero sequence current. The second point is that in the case of a 3-phase, 4-wire star system, there is a 4th terminal, which is the neutral line. We emphasize that under normal operation, it is well known that the current flowing through the neutral line is the vector sum of the currents flowing through the 3 phases, R, S, T. Of course, if the currents in those phases are equal, the current in the neutral line will be 0. However, in the case of unbalanced loads, where the currents in each phase differ, the current flowing through the neutral line will also be the vector sum of the 3 currents in the 3 phases R, S, T. We further emphasize that this applies to normal operating conditions, not during faults. Therefore, it is incorrect to refer to the neutral line current in this case as zero sequence current. As for the zero sequence current, it is indeed the current that flows through the neutral line, but only under the condition that it flows during unsymmetrical earth faults, whether it is a phase-to-ground fault or a phase-to-phase-to-ground fault. The second point is that for zero sequence current to appear, the neutral point must be grounded. Therefore, we emphasize that the only situation in which zero sequence current appears is during unsymmetrical earth faults. Thank you for your attention. See you in the next lecture.